Recording. Welcome back to your last in-class week in CE 312. My goal for this week is to end the class in the realm of reality, and that will become clear after the discussion today and the discussion on Wednesday. I want to make sure that we ground what we do in the real world, because after all, we are trying to be engineers. And so I think you'll understand what that means as we get into the topic for today. Real quick, I'm going to sort of very lightly gloss over the announcements, because before we get into the lecture today, I'm going to do some housekeeping for the class, because as you know, we're near the end. So I wanted to make sure that everybody was clear on what was happening over the next few days as we finish out CE 312. First off, the at-home game spreadsheet has been posted to Teams. If you remember, I think if you had me for statics, I did this in statics, and I'm doing it in here as well. There's a spreadsheet where what it will do is, if you put in your attendance grade, your homework grade, your project grade, your first two exam grades, it will tell you what your current grade is in the class, and that should match what's on Blackboard right now. But it will also back calculate what you need to get on the final to get an A, a B, a C, a D, etc. A buddy of mine in grad school called that playing the at-home game, so that's why I call it the at-home game spreadsheet. And so you can download that. Right now, the values in the cells are just dummy cells, so you can just replace that with what your grade is on Blackboard, in case you're interested. So let's talk about remaining housekeeping for this class. Okay, so. And by remaining housekeeping, I'm really talking about what I think matters most to you all in this room, which is your grade, right? Because that's what we're, I mean, I know you're here to learn, but you're like learning second. I want to know what I'm getting at the end of the semester. It's like first. And I heard a few chuckles on that one. Okay, so as you know, attendance is a grade in this class. All the attendance grades are up to date as of today. We have 3 more lectures remaining this week, obviously, so I'm going to be taking attendance for those days. I just did just now for today. So I'll probably start posting those, like the attendance grade for today. I'll probably post that today. I've been trying to do that throughout the semester, is post the attendance grades like the day of. So that attendance grade will change a little bit. Like if you miss some days and you're attending this week, that'll change. But just to keep that in mind. The analysis project, I started to grade that, but I didn't finish it. My goal was to grade that by Wednesday. And what I'm going to do is, much like the exams, I'll send you like a grade report that'll summarize like how your grade was computed and whatnot. But basically, I'm going to be looking at the 3 things. The 3 things being your Mastan, your CAD, and your calculations. And what I'll do in the analysis project grade report is I'll also take your submittal 1 grade and then put that on there as well, so you'll know just like, here's your grade on the project. And that'll match what Blackboard reports as your project grade. Sound good? Okay, so you'll know that at a super minimum by the end of the week. I'm going to hopefully try and get them done today, but I don't want to make too many promises. Homework assignments. Okay, so this is probably what I really want to make sure that everybody's clear on. So the current grading status, everything up to 8.1 is graded, and all the grades are posted to Blackboard. That's done. Homeworks 8.2 to 8.4 are being graded. My TA is probably going to just try and knock all this out this week. Homework 8.5 was due today. You just submitted that, hopefully. That was due today. Homework, we have 2 more homework assignments. I'm assigning a homework today, which actually has some bonus points possible on it. This is a homework assignment on AIDS for structural analysis. You'll understand what that means here in a little bit. That's going to be due Wednesday. Then there's a homework Wednesday due Friday. But our final is very early. So for this last homework assignment, this homework 9.2, it's due Friday. I'm giving you the solution right at 10 a.m. so that you have it to study for the final. So that means if I'm uploading the solution at 10 a.m., I can't accept late submissions, okay? So you got to have it in by 10 a.m. or I'm not accepting it, so because you'll have the answer. There is 1 bonus assignment, so I am going to ask that everybody do their course eval. Again, you could say I'm the worst professor ever. You could say his math jokes are horrible and he needs to derive some new ones. I know, I'm a dork. But in all seriousness, I do want to make sure that you feel like you're getting your money's worth. If there's anything that you think needs to improve in this class and future offerings, let me know. I am going to do the course eval survey during the final, where you rank the outcomes. You've probably done that in other courses. I'm going to do that here as well. And I'm probably going to give you some additional questions specifically about the project. As I've said, this is my first time doing this project in this course, and I really want to get your feedback on that. And I believe that the course eval university survey closes on Friday, but I'm going to give you until Monday to upload a screenshot. And to be crystal clear, I don't want to know what you said. Again, you say I'm the worst professor ever. I just want to see proof that you did it, okay? And so what I will do is add 10 points on top of your homework average. So can you get a homework average over 100%? Yes, okay? So just want to make sure that's clear. So if you've got like a perfect homework average right now and you do this bonus assignment, your homework average will be over 100%. So just be aware of that. What else? Okay, remaining schedule. So today we're going to talk about aids for structural analysis. Wednesday we're going to talk about tributary area, and you've kind of already done a little bit with tributary area because you needed to do that for the truss assignment. But what I want to do is take the concept of tributary area and apply it to a more robust system. In other words, how would you use the concept of tributary area to design or analyze the beams and columns in, let's say, this building or any building or bridge or something like that? I want to take that and make it a little bit more of a robust assessment. And then we're going to do our exam review on Friday. Speaking of, the exam is going to be on Monday, December 6th. It's from 10:15 to 12:15 p.m., but I'm not designing this like it's not any longer than any of the other tests. To me, it's just another test. It's not comprehensive. It's just on the stuff we've covered since exam 2. So it's similar logistics, similar operation. It'll be designed to be 50 minutes long. A couple things that are noteworthy. So what's going to be on the exam are influence lines, mass stand, and what we've been doing for this week. And I'll go ahead and answer one question. Are you going to have to use mass tan on the exam? I wrestled with this because I really wanted you to do a mass tan problem for the final, but what I've noticed is that I think for the vast majority of people in the class, they didn't have any problems installing mass tan, but there were a couple that did. And to be clear, I think it was better than last year, because last year we were using a different program, and every single person in the class that had an Apple product had significant problems running Recess. So I think that things went better, but there's still, I don't know if it's laptop issues or Windows not being updated, but there was a couple of you that had some problems installing Mastan, and I don't want to hold that against you. So I'm not going to tell you what the problem is on the exam, but the best way of describing it is it's going to be sort of an elongated conceptual problem related to Mastan. So you won't actually need Mastan to answer the question on the exam. I am going to do the CLO survey during the final as well. So again, I've been doing this class for a long time. I've never really had any time issues on the final. It's never really been a time crunch. Okay, I'm going to stop for a sec. Anybody have any questions about the housekeeping to end this course? Okay, let's talk about this topic, aids for structural analysis. And I'll be honest, this is not a typical lecture that you'll find in a structural analysis course. When I took structural analysis, this was not covered. And then I got to steel design and concrete design, and oh, here are these structural analysis aids. Just use them. What the heck are these, you know? And I think that they're very easy to understand the concept, but I think that in order to have a respect for what they are and what they're doing for you, I think they deserve a little bit of discussion. And like I said, I want to end this course in the realm of reality. Okay, what do I mean by that? I want to take a look at these two problems. These are some problems that we've done in this course, or at least very similar problems. Now, I've got beams with a The overhanging beam, I've got concentrated moments, distributed loads, internal hinges, triangular loads. You ain't doing that in real life. I'm just going to level with you. Not happening. Not happening. Now, let me be clear. This set of examples and what we've been doing this semester are necessary. There are components to these problems that you will need to deal with in real life. You do need to understand internal hinges to be able to draw influence lines, which are very real applications. You need to understand triangular loads for snow drifts and hydrostatic effects. Those are real loads that you will see in the real world. But these particular problems, not happening. They're just not happening. Have we been wasting our time? Of course not. These structures have served a very strong educational purpose, because the idea is that if you can do this, you can certainly do the routine stuff. You can certainly do the bread and butter analyses that engineers perform all the time. Okay, so you know, it's like, you know, if you're weight training, you know, if anybody's ever done any weight training, you know, and I'm going to make up some numbers, but if you get to a point where you can bench press, I don't know, 200 pounds, right? Then if somebody asks you to bench press 50 pounds, oh, that's easy, right? Because you've tested and expanded your limits so that the simple stuff is truly that simple, okay? But let's talk about some simple stuff. Let's talk about some bread and butter analyses that you're going to perform all the time, okay? Let's take a look at these problems, okay? Now, I have a cantilevered beam over here on the left that has a uniformly distributed load. It's 25 foot long, and it has 3 kips per foot on it. Now let's look at the beam on the right. I have a cantilevered beam. It's 37 foot long. It has a distributed load of 1.95 kips per foot. Is there really any difference between these two problems? No. I would argue that these are the same problems with just different numerical inputs, right? It's a cantilevered beam with a uniformly distributed load. Wouldn't it be valuable if I had a tool that could tell me what the results are for any cantilevered beam, for any uniformly distributed load? And if I have that, I can use that routine analysis aid over and over again for these routine computations. And this is a very routine problem. You have a cantilevered beam, it has to be able to support its own self-weight. Boom, there's the problem right there. Engineers deal with that all the time, okay? Simply supported beam, uniformly distributed load. That's going to be the function of your homework assignment. Common. Engineers do that all the time, okay? So let's talk about analysis aids. This is an analysis aid, okay? You can Google this right now. If you literally Google shears, moments, and deflections, this is one of the first results that pops out. What you will find is that many code spec bodies will generate these. And first off, there's nothing really special about this. You can probably find this on Wikipedia or just a Google image search. But I like this one. This is from AWC, the American Wood Council. So if you're designing timber structures, they have a Design Aid 6. Design Aid 6 is just shears, moments, and deflections for typical loading scenarios. And so this is scenario 12, figure 12. Cantilevered beam, uniformly distributed load. So look how they've structured this out. They've said, here's a cantilevered beam with a uniformly distributed load. Here's what the shear diagram looks like. Constant load, linear shear diagram, parabolic moment diagram. Look what they've given us. Here's the reaction. Here's the shear as a function of x. Here's the moment as a function of x. Here's M max. Here's shear max. Here's the deflection, the maximum deflection. Here's the deflection as a function of x. The whole problem solved for you. All you have to do is plug and chug. Boom, there you go. Now, these aids are neutral with regards to a unit system. So one of the things you will not see in the deflection equations is 1728. You will not see 144 times 180 over pi. The idea is that You use these equations for whatever unit system you want, and if you want to use conventional US units, you use the 1728. So when we derive expressions, we won't account for the 1728. You, as the analyst, do that when you're using them. You got to be careful when using these aids, though. In some instances, this is from the steel manual. The steel manual has these aids inside them as well. In this case, so here we have a simply supported beam, but we have a triangular load. You got to be careful for what the terms are, okay? So here, the best way of just pointing this out, here's the simply supported beam, here's the triangular load. Look at R1 and R2. R1 and R2 are the reactions. And it's saying that R1 is W over 3 and R2 is 2W over 3. But W is not this, okay? W is the total amount of load. So W is 1/2 base times height of this triangle. So you got to be kind of careful when you just plug and chug values in. And I would say that the most care needs to be exercised when you're dealing with triangular effects, because what they use for W is usually the total magnitude of load, not this magnitude at the top. Just be kind of careful on that. All right. Any questions? All right. One other thing that you need to be careful of is careful when adding terms from multiple analysis aids. Okay, so check this out. This is a simply supported beam, and I have a uniformly distributed load across the entire beam, but then I have a 17 kip load. But look, that 17 kip load, it's not at midspan, right? The 17 kip load is kind of off, right? Everybody see that? So here's my point. If you look at the uniformly distributed load and pull up the analysis aid, it says the maximum moment is WL squared over 8. So you take this W, this L, this times this squared divided by 8, that'll give you the maximum bending moment. If you take the point load, you can say, here's the point load, this is P, and it tells you what A and B are. A and B are just these two dimensions here. P times AB over L, that tells you the maximum moment. But the problem is they don't occur at the same spot. For the distributed load, the maximum moment occurs here, but for the point load, the maximum moment occurs at the point of the load application. So you can't just say that the maximum bending moment is this plus this. That doesn't make sense because they're not at the same spot, right? What you have to do is you can handle it a couple different ways. You can actually add the functions, the m of x for the distributed load, the m of x for the point load. You actually add those functions and then differentiate to get the shear function, set that equal to 0, solve for x, plug that value of x in, you know, like the whole calculus approach. Or what you can do is plot the moment diagrams in Excel for each of those functions, add them up, and then see where the max is. So I just be careful when maximum moments don't occur at the same spot. If this 17 kip load was at midspan, then you could just add this and this because the maximum moment would be at the same spot. Does that make sense? Any questions? In order to fully understand this, I would like to derive analysis aid expressions for this. A cantilevered beam subjected to a uniformly distributed load. We are going to determine the reactions, the shears, the moments, and deflections if we have time. So okay. Okay, so here's our cantilevered beam. with a distributed load. Now, if you remember when I recorded the results video for exam 2, I said one of the things you kind of got to stop being afraid of is X. We are going to see some variables here, so be aware of that. But there are reasons for that. There are reasons that engineers would throw the letter X around. This is one of them, okay? So this is going to get symbolic. We're going to live in alphabet soup a little bit. So we have a beam that's L long, subjected to a W distributed load, right? And what we'll do is we'll say that we have a vertical reaction and a moment reaction. Now, I would argue that this reaction and this reaction are a function of W and L, right? So maybe one way of looking at it is to say that my You're a tough crowd this morning. But in all seriousness, I know that this might seem like I'm being facetious, but there actually is some truth to this, that every equation that we derive should be a function of W and L, right? So let's handle this. Here, I'll get rid of this. Let's handle this like we would any problem, okay? What can I do with this distributed load? I collapse it into a point load. What is the magnitude of that point load? WL. Make sure that you're familiar with that. This is WL. And what is this dimension right here? 1/2 L. So if I sum forces in the y direction, help me out. So if I sum forces in the y direction, what do I have going up? I have RV. What do I have going down? So this is WL. Boom. There's a formula right there. So no need to do any statics or any analysis. Given a cantilevered beam with a uniformly distributed load, the vertical reaction is WL. Just plug and chug. What about the bending moment? Let's sum moments at the support. So what do we have? We have RM going like this. And what do we have here? How do we define a moment? It's a force times a distance. What's the force? What's the distance? What's the force? WL. And what's the distance? All right. WL squared over 2. Is that fair? What do we think? So let's continue on with this. I start at 0 for my shear diagram. What does my shear diagram do from left to right? Down in a straight line to what? What's the point it goes down to right here? WL. And then that reaction kicks it back up to 0, right? What is the area of this triangle? WL squared over 2. 1/2 L times that. Right? That's the area. So I go to 0, and what does it look like? It goes little to a lot, something like that. I'll do better than that. Hold on. There's your shear diagram. There's your moment diagram. What do you think? What if I wanted the shear here, or the moment here? Maybe I ought to cut a section, right? Let's test some of those skills that we developed during exam 2. How many functions are needed to fully define this moment diagram and shear diagram? 1. So we just need to cut an arbitrary section. Now, notice how there's no coordinate system here. Where should you put the coordinate system? Remember those little Dr. Mike's tips and tricks? To the left, right? On the free end. Cut a section, look towards the free end, remember? So we'll put our coordinate system right here. And we'll cut a section, look that way. So when we cut a section and look that way, here's the section, right? This is W. How long is this segment here? X. So collapse this into a load that's how much? And this dimension here. I cut a section and look to the left. Which way is positive shear? Down. Exactly right, down. So which way is positive moment? There we go. Same process. Down is V, down is WX, right? Right? How about summing moments at the cut. We have M going like this. WX times X over 2 going like that. Did I do that too fast, or are you okay with that? So am I okay with this? So let's just summarize so far. By the way, from our shear diagram, what is the largest magnitude of shear? The negative WL, right? What's the largest magnitude of moment? That right there, right? So let's just see something. Would you agree with this, that think about what's inside that box. We never have to draw a shear and moment diagram for a cantilevered beam under a uniformly distributed load ever again. That's what that box is giving us. We just did it. That's it for every permutation of cantilevered beam with a uniformly distributed load. Every one. You want the maximum bending moment? Boom. Right there. You want the shear at some random point on the beam? Boom. There you go. That's what it gives you. Why am I having you do this? Here's why I'm having you do this. Look familiar? Here's the reaction, WL. Shear is a function of X. M is a function of X. Maximum moment, maximum shear. I want you to understand where these equations come from, that they're not just miracling themselves onto a sheet of paper, that they came from somewhere. Does that make sense? Now, we're not done, because I want to see what we can get here. The maximum deflection. How'd they do that? Well, what method have we been using to compute deflection this entire semester? The method of virtual work. When we use the method of virtual work, we are required to do a real analysis, and we are required to do a virtual analysis. How does the virtual analysis work if I wanted to find deflection at the free end? Remind me, what do you do? Say it again. Pick a point of interest, in this case the free end, and then what?
The load of 1.
Remove all the loads, put a load of 1 at the point of interest in the assumed direction of displacement, right? So which way do you think that this point is going to deflect, up or down? Down. So let's see what happens. Okay? Now, recall, we already have a real moment function. We just did that, right? So what about a virtual moment function? So real moment W over 2x squared, which, by the way, here's something I didn't do. Can anybody look at these? Does this pass the smell test? What is the derivative of this? It's that, right? So that's another check that this is right. So virtual moment, oh, by the way, this is from 0 to L. So we need a virtual moment function, right? So what's the virtual structure look like? Well, it's this. And we place a single unit load, right? And then what do? Cut a section. Look that way. Positive shear. Positive moment. I only care about the virtual moment. So over here, let's just make sure that we recognize this is all we care about. We have our virtual moment. What else do we have? 1 times x on the left or right side? So 0 is m plus x, or m is minus x, right? Valid from 0 to L, right? So m is that, little m is that. What is little m times big M? Positive W over 2, what is that, x to the third? Is that fair? And so how do we determine deflection at the free end? What do? Deflection at the free end is the summation of all of our integrals of little m, big M over EI dx. Isn't that the method we've been using? So we only need one integral, right? And so what are we integrating? We're integrating this from 0 to L, but what did I forget? I got to have my 1 over EI, right? Because we're integrating little m, big M over EI. Is that okay? So what do? How do you do an integral like this? So this is an integral with respect to x. So everything that isn't x is a constant, right? So I can factor the 2 out and I can factor the w out. So then it becomes an integral of this, and now it's just an integral of x to the third. Now you better be able to do that. What is the integral of x to the third? X to the fourth over 4. So this is evaluated from 0 to L, right? So first off, I can factor out that 1/4, and then plug in the top number minus plug in the bottom number. What do you think? Does that match? WL to the fourth over 80I. And so how would you use this in the real world, right? Well, what you would do is, let's say this problem on the left. So W is 3, L is 2, E could be 29,000 KSI, I could be, 600 inches to the fourth. Just plug and chug and multiply by 1728. There's your deflection. That's it. Now, is there anybody in here that's curious how you do this? Like, how do you do this? This is the deflection at the free end. This is the deflection anywhere. I'm going to show you how they do that, but I'm not going to make you do it, okay? I'm going to show you so that you understand. But does anybody have any questions on this? I want to stop to make sure that everybody understands how this works. Does everybody understand how this works? Structural engineers use this all the time. They use these all the time, okay? But I want you to have some respect for where they come from and how they use it. For example, if you take me for steel design next semester, when we get into beams, we will have simply supported beams with uniformly distributed loads near the end, and we will use those all the time, okay? And the maximum moment equation is WL squared over 8. Where did that come from? Well, it came from this. So I want to make sure that you have an appreciation for where this stuff comes from. Now, before we go into this last part, I think we're probably going to run out of time. I might do a little quick video on how to do this last part. I want to pull up the homework assignment because I want you to understand what we're going to do on the homework. So, because I said there was some bonus credit. So, here is homework 9.1. This is your homework assignment due Wednesday. So here's what we're going to do. This is a 10-point homework assignment, but you have the ability to earn 15 points if you choose to derive an expression for the deflection at midspan for this problem. This is a simply supported beam with a uniformly distributed load. I want you to determine everything that we just did in this example just now. The reactions, so there's no moment reaction because there's no cantilever support. It's just simple support. So I want the reaction, the shear as a function of x, the moment as a function of x, and I want the largest magnitude of shear and the largest magnitude of moment. And if you're interested, a bonus challenge. Derive an expression for the deflection at midspan, taking EI to be constant. Do exactly what we did here. Don't incorporate a 1728 unit conversion factor, but I will tell you that for your virtual analysis, your virtual structure would theoretically require 2 moment expressions, and so exploiting symmetry can make the problem a lot easier, okay? And what you should get is WL to the fourth over EI times some number. For example, the number here was 1/8. There is the number for simply supported beams with uniformly distributed loads. And to be crystal clear, you can probably look it up. I mean, it's an easy formula to find. I'm not after you being able to find it. I'm after you being able to derive it, okay? And you don't have to do it, so. Any questions? I will show you on a separate video how they do the deflection at any point. I'm not going to ask you to do that on the homework assignment, but I'll tell you what they do is they basically, in a sense, instead of placing the load at the free end, they place it at any point. And so the way that I have always done it is I introduce a new variable because I don't like mixing up my x's. I think it's easier. So I usually place the load at some distance a from the free end. And so it helps me differentiate what I'm integrating with respect to and what I'm not. And when you look at the function in the end, it looks exactly the same as what you get from the analysis aid. But you don't have to do that for the homework assignment, so don't worry about that. All right. Does anybody have any questions?
Do you want numbers or just formulas?
This is a formulas assignment. And again, the reason why is because I need you to know where this stuff comes from. I will go ahead and tell you next semester, and if you choose to take concrete design, this formula for MX, MMax, you will use a lot in those classes. And I don't want you to go, where the heck is that coming from? This is where it's coming from. That's all I got.